A system of equations having infinitely many solutions. In prior videos, we have taken a look at systems of equations that have unique solutions, such as an ordered pair or an ordered triple, and also a system of equations that has no solution. In this video, we're going to take a look at different situations that have infinitely many solutions. In all of these situations, we are assuming that a system of equations was provided or created. Then that system of equations was placed into a matrix. And lastly, the matrix was reduced by hand or with technology with the Gauss-Jordan method or row-reduced echelon method. So in all of these examples, we're making that assumption. Let's start with situation 1. In situation 1, the bottom row of the matrix reduced with the Gauss-Jordan method will have all zeros. So the bottom row has zeros completely on the left and the right of the augmented line. This is interpreted as z equals any number. Now it's z in this case because my system of equations is 3 variable. We have x, y, and z. That third row is representing what z equals. So z is going to be any value. Now, yet frequently while that happens, the y and x variables will have limitations placed on the z values. So just because z can be any number doesn't mean x and y can be. And specifically in this case, we find out that in that first row, 1x will equal 4. So my equation is x equals 4. Then based on the second row, I have 1y minus 1z equals 1. Now y minus z equals 1 needs to be converted so that way it's just y equals 1 plus z. We add that z to the right-hand side, so we have y equals. Now z is any number. We went over that since the bottom row is all zeros. This is a general form of the solution of equations. But if I actually wanted to know an ordered triple that really truly worked for all of these, then I need to randomly guess a value for z. Okay, based on the information above, one of the infinitely many solutions can be found by selecting a value for z and then calculating y's value. I guessed z equals 3. Remember, z can be any number. So if z equals 3, then y will equal 1 plus 3. And that's because y equals 1 plus z. So y equals 4. And that means one of the infinitely many solutions is the ordered triple, 4 for x, and this should be a 4 for y, and then a 3 for z. So the ordered triple that I came up with is 4, 4, 3. I could find another ordered triple that satisfies this system of equations by picking a different value for z and then calculating what y would be. A second situation that has infinitely many solutions will be shown in this situation. Situation 2. The bottom row of the matrix reduced with the Gauss-Jordan method does have a solution, but the other rows in the matrix have infinitely many solutions. The example that I have is a matrix that has 2 rows, but it has 3 variables. In the bottom row, it tells us that z will equal negative 2. So we know z equals negative 2, but that first row tells us that 1x minus 7y will equal 5. That first equation from the first row needs to be transformed. So it says x equals, and it'll be 5 plus 7y. So we know z equals negative 2 from the second row. But what we don't know is what y equals. There's no row for y. That tells us that y can be any value. And in this case, the matrix has a column for y, but no stated solution. So that's why y can be any value. All right, so these are our general solutions. X is going to equal 5 plus 7y, and y will equal any value. Z will be negative 2. So based on that information, one of the infinitely many solutions can be found by selecting a value for y and then calculating x's value. In this case, I let y equal 6. I randomly pick a number for y because y can be any number. Since y can equal 6 and I know x equals 5 plus 7y, I can put that 6 for y. Following my order of operations, I find out x equals 47. All right, this means one of the infinitely many solutions is the ordered triple 47 for x, 6 for y, and -2 for z.